Hello, welcome back. Welcome back. Sparse crowd today. I hope it wasn't the midterm that has gotten everybody kept away. How was the midterm? Didn't like it. It was. I understand that a lot of you took most of the 2 hours to do the exam. It's a good thing we didn't give you the one that we originally wrote, which is probably at least 50 or 75% longer than that. So we cut it down quite a bit. There's only one handout today, and it's another set of lecture notes. We're going to be working on grading the midterms. We'll try to get them back next week, but may not be able to do that. You should be working on the second programming assignment due next Tuesday. Is that all going well? No problems, no glitches with systems and the Verilog and all of that? Okay, sounds good. I was lax in assigning a homework last time, so we should do that. So let's assign homework number 4. It's mostly right from the book, but there will be a few changes. And this will be due on Tuesday, so you get a week and a half, February 28th. That's right. These are Chapter 5 problems. The first one is 5.4. The second set is 5.7 and 5.8, and I think there's a reference to a non-existent figure or a figure table from a previous edition of the book or something like that. For those problems, you should use the table on page 217. And then problem 5.10, and for that one you should use as a reference figure 4.25, and in particular the part of that figure that deals with DLX, not the part that deals with VAX and other ugly machines. And then another set having to do with stuff we'll be talking about today and next time, 5.30 and 5.31. Now we will also be posting some clarifications to some of these problems on the news group. So they're not there yet, but in a day or two, read the news group for some clarifications to those questions. I'll leave that on for a few more seconds so that you can get that down. I try to have everything like this on the notes, part of the handout, but not always possible to do that. And of course the programming assignment due next Tuesday. Any other questions, comments before we go ahead? Okay, last time, a week ago, we were talking about something that you probably don't remember anything about because I told you it wasn't on the midterm, which is scoreboarding, this way of doing dynamic instruction execution in a way that the instructions don't have to be executed in order. And just to refresh your memory, let's take another look at the block diagram of the way the scoreboard works. If you remember, there are multiple functional units. They all reference the register file. They read their operands from the register file and write back operands to the register file. There's no forwarding in this kind of picture. The instructions, a batch of them, get held in the scoreboard until they can be issued, and they get issued in whatever order they're allowed to execute in. As soon as their operands are ready, as soon as their operands have been written back to the register file, then their functional units are told to go ahead, read the operands, compute the results, and write the results back. So in the scoreboard, they wait for the true data dependencies, for the read-after-write hazards to clear. That works great. The part of this that doesn't work so great is that we still have write-after-write and write-after-read hazards, because there's only one copy of the registers. We're not doing the kind of software trick that we talked about once before of register renaming, so that every time you write a register, you can't do that right until you're sure that all previous reads have completed. So in particular, in the write-back stage, the functional unit is sitting there with its result, ready to do something else, but it can't hand off the result to anything because There may be a register, the register that it's about to write may be in the register file waiting to be read by another functional unit which is waiting for something else. So everybody stacks up waiting for this guy to get rid of his result and put it into the register file. So the question is, can we do better than that? Can we get rid of these, in particular, write after read hazards in a way that's analogous to what we did in software by renaming registers? And the answer, of course, is yes. And the next mechanism we're going to describe will show how to do that. Before I do that, the machine that we're going to be discussing is the 36091, basically, which came out in the late 60s and had this Tomasulo's algorithm, which is what we're going to be discussing in it. And for this week's show and tell, I'm going to hand out the original copy. I think this is the first place where, in at least semi-public form, the Tomasulo algorithm was described, which is the theory of operation manual that IBM provided with the 36091 machine. We actually had a 36091 here at Stanford for many years, and it was the premier machine that physicists up at SLAC and other number crunching people were using for many years. This manual is interesting on two regards. One is that it describes the Tomasulo algorithm, or at least tries to, and the other is it demonstrates the high level of internal documentation that IBM maintained for all of their machines. This is one of about 25 manuals that were describing the high-level operation of that machine. Somebody once told me, and I believe that it's true, that at the time, in the mid-60s, IBM was the second largest publisher in the world with respect to the number of different publications that were produced, second only to the U.S. federal government. And I think that's probably true. The other fascinating thing about the 91 was that it was sort of the last classic machine with a wonderful big front panel. It had a front panel that was about 8 feet wide by about 3 feet high that was crammed full of lights and switches and knobs and buttons, and it was a hacker's delight. It was a wonderful machine to play with. It was the kind of machine that you really could take a movie of or a picture of, and it looked like a computer. These days, computers look like boxes with nothing in them except a keyboard and a screen in front of them, so they're not quite as exciting. But the 36091 is dead, but the algorithm that was invented for that machine, the Tomasulo's algorithm, is not dead by any means. In fact, it's having a recent resurgence, and we'll talk about where it's appearing in the latest chips that you can't even buy yet. Basically, the idea behind Tomasulo's algorithm is to try to put into hardware the kind of register renaming that we looked at before in software. Basically, the idea is that every time you write to a register number, you allocate a new physical register. After all, you're about to put a new value into it. The old value can be saved for anybody who still wants to use it, but you can allocate a new physical register for that new value and keep the old physical register for guys who need the old value but haven't yet read it yet. In a way, it's like the Mad Hatter's Tea Party. You know, every time you dirty a dish, you move to the next place to get a clean dish. Well, every time you write to a register, you write to a fresh register and leave behind the old register. Now, eventually, you have to recycle the old registers because you can't have an infinite supply of them. But this accomplishes the trick of register renaming. So what are the implications of this? Well, for one thing, it means that you need more physical registers than you really have register addresses. You may have 32 registers that your architecture can address. You've got a 5-bit field in the instruction format. But you may need more than 32 registers in the hardware, because every time you write to register 4, you're implicitly creating a new copy of register 4 to write the new result into, so that you can keep saving the old result. So you could imagine putting a stack behind every register, but that would be kind of excessive, because most of the time, most of them wouldn't be in use. Another kind of technique is to keep a pool of unassigned physical registers, and every time you need a new register, because you're about to write to one, you allocate a new register from this pool. And then every time you reference the original register number, you have to change that reference to be the new physical register that you got out of that pool. So you've got a set of registers and then some kind of a mapping function that gets you from the original register designation, which might be 5 bits, to this physical register designation, which might be more bits because there are more physical registers that you might have to reference. And then you've got to clean up. Eventually, you've got to wash the dishes. When the register is written, all previous physical registers that came from that same register number can be freed as soon as everybody who needs that value is done. So if I write a new copy of register 5, and the old copy of register 5 is hanging around because there are still some unfinished instructions that need to read it, I need to keep track of the fact that there are those unfinished instructions, and as soon as they're finished, I can sort of recycle the old version of register 5 and return it back into the pool. Now this sounds a little complicated, and in fact it is, and if you were to implement it exactly like this, it would require a lot of hardware, but in fact the beauty of the Tomasulo algorithm is that it's much simpler than it seems to be if you read a description like this, but has exactly the same effect. The big win, in comparison in particular to scoreboarding, is that we now don't have to stall for read after write and write after write hazards. Instead of waiting for a register to be read, you simply write a new copy of it and you get a fresh copy of it while the old copy is still around for the previous instructions to be able to reference. Just to bring this home, let's look at a piece of code and imagine in the software sense renaming the registers, but in fact we're just going to tag the registers with different numbers. Here's a case where we're doing a multiply into floating point register 0, and we have a read after write data dependency here. The store is going to be using floating point register 0. Well, that's not a problem. We do, however, have a problem here. We have a write after read dependency because the store uses register 4, but the add is going to deposit something into register 4. So in fact, imagine that these registers are the first versions of the floating point registers and fixed point registers, and I subscript them with an A. And then as soon as we need to write a new version into register 4, we assign a new register 4. This is register 4 sub B, which is a different physical register, although has the same designator. And even though the store might not have finished making its reference to register 4, it's referencing register 4A. We're storing into register 4B, no problem. But it also means that any subsequent use of register 4 after this instruction has to be register 4B, not register 4A. I should have shown that here, but somewhere else here there might be an instruction using register 4, and it has to use the B variant of register 4 and not the A variant of register 4. Basically just a way of tagging the registers to know which version of them we're referring to. Okay, so how do we actually do something like this in hardware? Well, let's see what's the best order to describe this in. Let me talk to the picture, although there's also a description in one of the slides about the various pieces of this picture. Basically, remember in the scoreboard system there was a table that kept track of the functional units and what their status was and which instructions were assigned to them and whether or not their operands were ready in the register file. In the Tomasulo algorithm, basically in front of the functional units there are one or more basically queue buffers called reservation stations, where instructions that are waiting to use that functional unit get queued. And as the instructions get issued, somewhere in here there's an instruction decode or instruction issue step, where instructions are fetched and dispatched to these various functional units according to what the opcode of the instruction is. As the instructions get issued to the functional units, it checks to see whether or not the registers that instruction needs as operands are ready, which is to say they're in the register file and no other instruction or functional unit is going to produce a new result for them. If that's true, then at the time the instruction is issued, that operand is read out of the register file and stored in the reservation station. In a sense, that makes the duplicate copy of the register, because the register that's in the register file is now free to be written by some subsequent instruction, because the instruction I just issued, which uses it, has already snarfed up a copy of the current value of that register. It's a little bit different from the way I described it before, where every time you write, you create a new copy of a register. Basically here, every time you issue an instruction, you make a copy of that original register, and that frees the register in the register file to be written to. So the one in the register file is the newer copy. The one in the reservation unit is the older copy. Now what happens, in fact, if I issue an instruction to this reservation unit, and the value of the register in the register file is not the right one, and it might not be the right one, let's say, because some functional unit for a previous instruction is computing a new value for that register file, for that register, and it's not yet written back into the register file. I can't fetch the old value from the register file because that would be wrong. So in fact, what I do is issue the instruction to the reservation unit and mark that operand as, number one, unavailable yet, so it can't get into the functional unit. But number two, I also mark it so I know which functional unit that register value is going to come from. So when it is produced, I can snag its value at the same time that it's being written back to the register file. In fact, this common data bus, this thick bus that you see running around the picture, is the way that you do that stuff at the same time. You may have an instruction executing in the functional unit that's about to change register 6, but you might have, let's say, 2 different instructions for that functional unit or for other functional units that are waiting for the result of the register 6 value. Well, what happens in this structure is that when the functional unit finishes, it puts out its answer, and it puts out an indication of what unit produced that answer, namely this functional unit, and everybody in the system who might need that result listens to this broadcast value on the common data bus. There's an instruction sitting in here saying, I needed the result of functional unit number 2. When it finishes and broadcasts its result, it grabs it. At the same time, any other instruction in any other reservation station does the same thing, and at the same time, that result gets written back to the register file, so its final value gets updated. Is that a question? No. Okay, sorry. We'll see this in a bit more detail. But one of the things you notice immediately is that this common data bus may in fact be a bottleneck, because there might be multiple functional units that are finishing at the same time, all trying to write their results onto the common data bus, and yes, indeed, that's a problem, and we have to deal with that. Notice that load instructions are treated just like any other functional unit, and if you were waiting for the result, if you're waiting for a register which is the result of a previous load, then you can get put in, you as an instruction, can get put into the reservation station with a mark saying, I'm waiting for the result which is going to appear in load buffer number 8. When the memory finally produces that result, it gets broadcast onto the common data bus. The instruction which is waiting for it in the reservation unit can grab it off the bus and be ready to execute. And at the same time, that value gets written back to the register file. So notice 2 things. One is that instructions get issued whether or not their functional units are busy. So in a sense, we've sidestepped the issue of structural hazards. The scoreboard, remember, didn't issue instructions unless that functional unit was free, because it didn't have this queue of reservation stations. It had to record the instruction in the functional unit that was going to execute it. So it had to stall on structural hazards. Here we don't. As long as there are reservation stations available, we issue the instruction into the reservation station, and it waits for its functional unit to become free. The second is we don't have write after read hazards, because we read the instruction, we read the operand early in the execution of the instruction at the time it's issued, and we do that in order of original instructions. Remember, this is in order issue, out of order execution. So because it's in order issue, and because we read the operands early on in the cycle, it has the same nice property as DLX. We can't have write after read hazards, because all the instructions were issued in the right order, and they all fetch their operands in the right order, so the order in which writes happen later on doesn't matter. So we've avoided, or at least postponed, structural hazards. We've avoided write after read and write after write hazards. We've gotten out of order execution. And we have a couple of minor problems, like contention for this common data bus. Okay so far? Okay, let's look at the pipeline stages for a machine that might use Tomasulo's algorithm. Basically what's happened is that we've taken what used to be the scoreboard and register fetch stage and essentially put register fetch into instruction decode like it was with DLX and done the scoreboarding function during the reservation station phase. Describing this as a pipeline gets to be a little bit strange because in fact things get out of order toward the end of the pipeline, but it still is a pipeline in the sense that only one instruction is fetched at a time, only one instruction is decoded and assigned to a reservation station at a time. The only thing that will stall instruction decode in this case is a reservation station unavailable problem. If a particular instruction is destined for a functional units and all of the reservation units in front of its that functional unit is full, then instruction decode and instruction fetch have to stall and wait until that reservation station is available. If that's not the case, though, it does this operand fetch and assigns it to a reservation station. Now, this is fetch in quotation marks, because if the register is available in the register file, if the correct value, correct version number of that register is available, then it fetches the operand itself, the numerical value of that register, and puts it into the reservation station. If it's not, then it puts into the reservation station a pointer to where that result is going to come from, so that when it gets broadcast on the common data bus, it can grab it. So once it's in the reservation station, it just hangs around waiting for read after write hazards to clear, which is to say waiting to get the results that it didn't get out of the register file. And as soon as it's ready, it then waits to get into the execute. There may be more than one instruction sitting in the reservation station, all of whose hazards have cleared, so they all have their operands, and they just wait to get into the execute phase and use the functional unit and produce their result. When they're done, they have to write the results back to that common data bus so that other reservation stations can grab it, and also back to the register file, and they have to be the exclusive owner of the common data bus in order to be able to do that. So just to summarize, we eliminate or deal with, we don't eliminate, but we deal with the read after write hazards by delaying in the reservation station until their operands are ready. We eliminate the write after read hazards by fetching the operands early and in the order in which the instructions are issued, like we did in the original DLX. And we eliminate write after write hazards by making sure that only the last instruction that's supposed to write to a register will actually update the register file. And we'll see how that works when we go through the details. But basically, we keep a record of who is supposed to be the functional unit that really leaves its value in the register. And if some other instruction happens to finish too late, and if it writes back its result destroying what should really be a later instruction's result, then it basically does a no-op. We'll see that in more detail. But basically, you keep a record of who it is that's really supposed to write that register, and all of the other people don't write their result to the register file, although they do broadcast it to the common data bus for other reservation stations. Yeah?
So that means that there's sort of like, the register is sort of like a receiver, just like all the reservation stations are waiting for a given value to come across on the bus. A given register slot would also be waiting for something.
It is waiting for something. In fact, you can view a register file very much like a reservation station operand entry, which either contains a value that's valid or it contains a pointer to a functional unit saying this is where my result is going to be coming from. And in fact, let's look at the, well, before we look at the data structures, let's look at a pipeline example, and then we'll actually look at the data structures that implement this. Okay, here's a simple example of beginning with a multiply instruction that takes 4 cycles, produces its result in register 0. So it goes through instruction fetch, instruction decode, queues up in a reservation station, goes through its 4 cycles of execution, arbitrates for the common data bus, and does its write back. And that write back is going to the register file in this case. Now the next instruction is using FP0. We have a classic read after write hazard. That instruction gets issued, hangs around in the reservation station for the appropriate functional unit, but one of its operands, in fact its only operand in this case, is marked as not yet available. Its result comes from the multiply instruction in its functional unit. So it hangs around in the reservation station until the write-back is finished, until the result has been broadcast on the common data bus. Then it can go into execute and do write-back. So this is kind of a classic read after write hazard elimination or dealing with it. The add instruction that follows, notice that the add instruction which follows is about to destroy register 4. That's not a problem. Even if the store instruction hasn't yet executed or hasn't yet used its value of register 4, it doesn't matter, because it copied that value of register 4 out of the register file into its reservation unit at the time that it went into the reservation unit, which is here. The add can destroy register 4 anytime it likes to after that without worrying about destroying what the store instruction is going to need. So the add instruction goes through its reservation cycle, goes into execution, is ready to write back its result. The problem here is we have a structural fault, because both of these instructions, the multiply and the add, are trying to get to the common data bus at the same time. In that case, the add instruction has to stall, do its write back later. So we had a write after read hazard here. Similarly, for the load instruction, well, the load instruction could be a write after write hazard, because it's writing the same register that the original multiply is writing. But there are no read after write hazards to stall it. So it goes, and assuming that there are not functional units, it goes into the reservation station, immediately proceeds into execution, tries to do its write back. Again, conflicts with the previous add for access to the common data bus, so it has to delay one cycle. Now in this particular case, the load is finishing after the multiply, so we wouldn't have a write after write problem. If for some reason the multiply took a long time, if the multiply took 8 cycles instead of 4 cycles, this would all still work. And what would happen is that the multiply would be marked to not actually do the store into FP0. Because remember I said that the person to store into the register file, or the instruction to store into the register file, is the last instruction which is a valid writer of that register. So this load instruction would do its store, its write back into the register file down here. The multiply instruction, when it got ready to do the write back, would do it in cycle 12, but it wouldn't be written to the register, because it wasn't the one which was supposed to leave its last value in the register. Now we do have another little minor problem here. Notice that these stores and loads are terminating out of order. So we did a store, and it executed, I don't know where you wanted to find the actual memory write as having occurred. Let's say it's at the end of execute, back here. A subsequent load instruction is loading some value from memory here, and let's say that it's referencing it back here or even back here, sometime in there. If they're different memory locations, that's not a problem. But if in fact they're the same memory location, which you can't tell certainly at compile time, and it's hard to tell by inspection, then this load would get the wrong value. And in fact there has to be special hardware in this kind of an architecture to dynamically compare the memory addresses of queued up stores and queued up loads to essentially forward the result of this store to this load, or better said, to delay the execution of this load until the store has taken effect. And that kind of memory problem we'll see in a second. Any questions on the pipeline? Okay. So what does the machine actually need to perform all of this magic? Well, unfortunately, a fair bit of hardware. But on the other hand, the 36091 was a machine that sold for about $6.5 million, so they could afford to put a fair bit of hardware in it. Basically what you need are two fundamental structures. One are the data structures for the reservation stations that keep track of what functional unit it is in front of. And this is a kind of primitive case where I have 3 adders and each one of them only has 1 reservation station at the front of it, and a couple of multipliers each with 1 unit. You need to know whether it's busy. You need to know what the specific opcode is that it's doing, because functional units do multiple things. And then you store for each of its source operands either the value that was read out of the register at the time the instruction was issued, or the tag. And the tag is a marker for a reservation station that's going to produce that result, which is to say a marker for a functional unit that's going to produce that result. Or a load buffer. Load buffers and functional units are very much the same in the sense that once conditioned by an instruction, they produce a result. So I've marked load buffers here as 1, 2, and 3, and reservation stations by the name, but basically there's got to be some kind of uniform naming sequence that says that this XX can refer to one of these functional units, or it can refer to one of these load buffers. Now, the other primary data structure we need is something that marks the registers in the register file, that says either nothing, which is to say no instruction is going to produce the result for that register, or it marks it with the number of a reservation station that will eventually produce that result. And that's what you can use to indicate that the value in that register file is essentially dead. It's an old value. It's one of the multiple copies that we've renamed that is now not the live copy. Okay, so what are the rules given that data structure? This is again is a kind of a semi-English translation of the more mathematical description that the book has for what the sequence of operations is. First, on issue, the only thing you have to wait for is a reservation station. If you've got a reservation station for that functional unit, then you assign it. If the source register has no result pending, if in that bottom table there's no entry saying that somebody else is about to write it, then you read the value from the register file. Otherwise, you set the tag in the reservation station to be the reservation station from which the result will eventually come, and then you wait for that result to be broadcast on the common data bus. And then we produce a result, so you set the register status for that register to be our station number, saying that we're about to produce a result for that register. Now note that there may be a previous instruction that had already been scheduled to produce a result for that register, and its number is in the register status. That doesn't matter. We're going to overwrite it. We're going to overwrite it to indicate that we're the latest instruction to produce a result to that register. So execution is easy. You wait until both source 1 and source 2 values are present, that the tags have been converted into values as they get taken from the common data bus, and you go into execution. In write back, you only have to wait until you can get a shot at this common data bus in order to be able to broadcast your result. And then you write to all the registers for which we're the destination, and you clear out the register status. All the registers. Can't think at the moment about why there should be more than one destination register for a particular functional unit. But I will think about that. There certainly can be one, our destination register, and you zero its register status. It's certainly the case that there may be multiple reservation stations or store buffers that list us as an operand tag that are waiting for us to produce the result. Stores are just like operands for functional units in the same way that loads are like results for functional units. So the store table keeps track of either the value to be stored or the number of the reservation station that's going to produce that value. So when we broadcast on the common data bus, the store buffers grab the result if it's for them, and the reservation stations waiting for operands grab the result if it's for them. So that's how it works. That's probably enough detail to write a program to make it work. Here's an example of the algorithm in progress. We're in the middle of executing this sequence of instructions. Notice that we don't have any data structure particularly that records the instructions, because all of the information is distributed in the reservation stations and in the register file. This register status, by the way, might actually be part of the register file. You don't have to think of it as a separate array. It might just be a marker indicating whether the register file has a value or not, and if it doesn't, that what's in the register file is a pointer to a reservation station. So where are we here? The first load got finished. The second load is finished and in execution, but has not yet produced its result. Its result is going back into register 2. So the status for register 2 indicates that load 2 functional unit is going to provide it. Load 2 load buffer, which is load buffer is like the destination part of a functional unit. So in fact, the load buffer number 2 is marked as busy and is currently fetching this address. Now there's a read after write hazard here for the multiply, for the subtract, and for the add. So notice that the multiply, the subtract, and the add all have load 2 listed as the tag part of their source field. So they're waiting for that functional unit, for that load buffer, to broadcast its result on the common data bus. And as soon as that happens, all 3 of those values will be filled into the reservation stations. And in fact, there's a lot of this kind of parallel operation that goes on in Tomasulo's algorithm, so that multiple instructions can be ready to execute, can be made ready to execute at the same time. And they can all proceed to their functional units simultaneously. So although we're issuing instructions 1 per cycle in order, we can start instructions executing multiple instructions at a time and out of order. And that's part of what the power of this algorithm is. Notice that once that happens, when that load finishes, this instruction, which is the subtract, now has values in both sources, and the multiply now has values in both sources. And those reservation stations are on separate functional units, so in fact both of those instructions will begin to execute simultaneously. In the meantime, in fact during the same write-back cycle, the load has broadcast its result on the common data bus, and it goes back to the register file. So any subsequent instructions to be issued that need it will read it directly out of the register file. And then that entry in the register status gets cleared in preparation for someone else who wants to, well, to indicate that that current value of the register is in the register file. And so on. Any questions about how this works? I think it's actually a simpler algorithm in a lot of ways than the scoreboarding algorithm. And in fact, it gains a lot more power because of the ability to get around read after write, write after write, and write after read hazards.
I have a question,
Yeah.
Not about how it works, but why are the floating point registers only numbered on even numbers? Is that because they're double sized?
Well, that's an interesting question. That's the way the 360 numbers its floating point registers. For some reason, number one, there are only 4 of them, which is an interesting problem. And number 2, they're numbered 0, 2, 4, and 6. And I guess the reason is because they're 64 bits wide, and the integer registers are 32 bits wide, and they're in pairs or something like that. It's a weak reason. There's really no reason. That's the way it was. And one of the neat things about Tomasulo's algorithm is that, assuming we can handle branches well, this does the execution time equivalent of loop unrolling. Remember, if we had a loop like this, one way to make this run faster is to unroll it so that we have 2 copies of the loop inside. And then we could reassign to register renaming so that the second copy of the loop uses different destination registers in the first copy. Instead of using F0 in the first copy, we might use F6 or some other unused register. And then we could reorder the instructions to optimally schedule them to get them executing with the maximum amount of overlap. Well, in fact, Tomasulo's algorithm does that automatically for us. It does the effect of register renaming by fetching operands early so that we're not stalling waiting for previous instructions to read their register values. So in fact, if we had 2 multiply units and we did the correct prediction of the branches, we could get 2 iterations of this loop executing in parallel automatically in the hardware. And in fact, it works that way.
Question.
So,
It seems like, though, that
yeah.
you're not eliminating the overhead of the loop due to the incrementing or decrementing of loop counters.
That's correct. And you're not eliminating the overhead of the loop for the branch itself. So there still may be a win to do software loop unrolling instead of hardware loop unrolling. But in fact, we will talk later today about schemes for making branches better. And we can do a lot of that in hardware as well as software. Okay, so what are, in summary, the good things and bad things about the Tomasulo algorithm? Well, one is you still need some way to access the common data bus and to resolve that conflict. And in fact, the other conflict that exists is the access to functional units. In particular, if there's more than one reservation station, there may be more than one instruction ready to execute in that functional unit, and you have to somehow decide which one to go first. The manual I'm circulating around, in fact, shows that the 36091 had a fairly complex scheme, which was a combination of FIFO and a priority-based scheme for both access to the common data bus and access to the functional units when they had more than one reservation station. And they were trying to even further optimize the progress of the machine by giving the common data bus preferentially to the instruction or to the result which was needed by more operands and more functional units. And I'm sure that's a good thing to do. I'm not sure it was worth the pain that they went through to do it. As I pointed out, one of the hazards that we've introduced is a memory hazard. We now must check in the store buffer for loads that are loading results that are in the store buffer but haven't yet been stored. The book and other people call this dynamic memory disambiguation. I don't like that name because there's nothing ambiguous about it, but it's a classic kind of hazard that we have to watch out for. Obviously, it increases parallelism because it's doing dynamic scheduling. It's executing instructions out of order based on whenever their operands happen to be ready. We've eliminated right after read and right after write hazards by, in effect, register renaming, having multiple copies of registers by storing them in the register files, in the reservation units. And basically allows you to simulate the effect of having more registers without having the compiler or the programmer having to allocate additional registers, actually use them. And it turns out that the 360 for which this algorithm was originally designed was a classic case of why you needed that. You were asking why the registers were given even register designators. An even more fascinating question is why there were only 4 of them. In fact, there was a 4-bit field for register numbers, and there were 16 integer registers, and there could have been 16 floating point registers. And in fact, the original architecture, which on the whole has very few mistakes, I think had that as a mistake, that the architecture defined there to be only 4 floating point registers. And all programs and compilers were written to assume only 4 floating point registers. Because of that, it was very hard to take advantage of compiler techniques like loop unrolling and register renaming, because there weren't enough registers to rename among. You only had 4. And this Tomasulo algorithm allows you to get the effect of having lots of registers, even though your instructions only get to name 4 of those registers. Yeah.
If it actually has all those registers and there's enough bits in instruction, and what's the reasoning for not doing
it doesn't have all of those registers. It has all the fixed point registers. It has 16 fixed point registers. The floating point registers are separate. It uses the same, I think, it uses the same field in the instruction for floating point instructions to indicate a register number. And I don't know why.
But effectively, with Tomasulo's algorithm, you have extra registers.
Right. Well, remember, the architecture definition came way before Tomasulo's algorithm. The architecture was defined for much simpler machines in 62, 63. The Tomasulo algorithm came out in 67 or something like that for the 36091, the high performance implementation. And the challenge was how to make a high performance implementation of this instruction set architecture that wasn't great for that particular purpose. I don't know the answer to that. Maybe we should ask Mike Flynn, because in fact Mike Flynn was essentially the head of the design team for the 36091, and Tomasulo worked for him at the time. And maybe he understands why it is that the architecture only defined 4 floating point registers. So those are the advantages. What are the disadvantages? Well, it takes a lot of hardware. There's a lot of parallel comparisons going on. All the functional units and all the store buffers are comparing very much like operand forwarding that we saw in the DLX pipeline, but to the nth degree. They're doing lots of parallel comparisons. Imprecise interrupts are a real hazard in this machine, like they are in any machine that does out of order execution. And in fact, the 36091 did not solve that problem. It basically had imprecise interrupts, and if you had a floating point failure, the machine sort of skidded to a halt and left no trail about what had been done and what had not been done. But we now know how to do that better. We discussed about reorder buffers or the equivalent, and new implementations of machines with Tomasulo's algorithm, in fact, typically include something like a reorder buffer for many reasons, but one of them is to make interrupts precise. Branch hazards are still a problem because we're getting the machine to run really fast in sections of code between branches, but then the branch penalty is becoming an increasingly large fraction of our performance problems. And in fact, that leads nicely into the next section, which has to do with making branches go faster. And unless there are questions, we will get into that. Now, so far we've gotten our machine to be pretty good, pretty fast, in the sense of executing instructions at about the maximum rate we can. Not quite true. We're still only issuing instructions once every cycle. And in fact, after we talk about branches, we'll talk about a way to even get around that. But we're issuing instructions once a cycle. We're executing them as fast as the read after write hazards will allow us to do. And that leaves us in the position where the next step to get the machine to go even faster is to do something even more clever about branches. Because of what we've done with dynamic scheduling, the effect of data hazards is getting smaller. Pipelines are getting deeper. And we're going to gradually, as I mentioned, move to multiple issue instruction scheduling, where on each cycle you can issue more than one instruction at a time. So all of the instructions between branches are getting done in a smaller and smaller amount of time, and branches aren't getting faster. So we need somehow to reduce the branch delay better than we were doing before. What we've talked about so far are branch delay slots. Well, that works okay if you're trying to cover up a single cycle delay. We can make certain assumptions about conditional branches. We've seen about either them being taken or not taken, and probably the best we can do in a static prediction sense is to guess that backward branches are taken because they're loop closures, and that forward branches are not taken or may be taken depending on which side of 50% you think they're on. They are. The other is that, and I mentioned this before, that the compiler or even the programmer might have a much better idea whether particular conditional branches are going to go or not. The other interesting approach is to let the program tell you what the results are for each particular instruction. All of these things are based on looking at a particular instruction and guessing which way it's going to go most of the time. So you can run your program once, and with an interpreter or some kind of instrumentation, basically count for each conditional branch how many times it goes, how many times it doesn't go, and then compile your program again and leave behind in each one of those branch instructions a bit that tells the machine what the odds are for this particular instruction. And in fact, that does pretty well. If you look at the next slide, you see a chart of misprediction frequency, the percent of times where you get the wrong guess for the branch. If you guess in a constant way, which is always guess that backward branches are taken and forward branches are not, you get the gray bars, which range from, well, in reasonable cases, from 15% up to 70%. But if you just execute the program once and store with each branch a single bit saying whether that branch most of the time branched or didn't branch, that's this profiled case, then you get dramatically better results. In some cases, 8% versus 70%, because some of those backward branches are not loop closures. Yeah.
Couldn't the compiler just reorder the instructions so that it always, so it would flip the taken versus not taken?
It can do that in some cases. If they're if-then-else's, then it can often do that just by switching the two blocks. If they're backward branches for loops, that gets a little bit harder. Or in general, if it's spaghetti code, which people tend still to write, it gets harder and harder to do that. But yes, a compiler that knew that the machine was making a constant prediction could do that. An even better approach is to mark each instruction based on what its history was the last time you executed it. And that's actually pretty good. We'll go through a scheme, in fact, that does that automatically without having you have to run the program twice. And this is operationally a little bit complicated because you wind up compiling the program, running the program, saving some runtime tables that then get fed back into the compiler for the next version of the compilation. It works, but it's not the kind of thing that people like to do very much. So the alternative to that kind of static branch prediction is dynamic branch prediction techniques. And we'll look at a couple of different elaborations of it, where basically that history, the kind of history that profiling gathers at execution time and feeds back to compile time, that history can be automatically accumulated by the hardware as it executes and then used for subsequent predictions of branches. But we always got to keep in mind that the prediction itself can't take too long, because if it takes too long, then you might as well just wait for the branch to decide. So you've got to make sure that whatever you're doing has got to be very fast and occur early in the pipeline, otherwise why bother doing it? The other thing is that the effect of predicting wrong must be smaller than doing no prediction at all. I mean, if by doing this prediction you've increased the penalty of a wrong prediction and you don't get enough hits, your success rate is too small, then you will have slowed down the machine rather than made it faster. Okay, so let's look at the first example, which is to keep a table for each branch somehow, dynamically in the hardware, and you record the history of that particular branch. One simple way to do that is to keep a little cache, which is, well, you could say that it's an array indexed by the address of the branch. Now, obviously, you can't afford to keep an array which is that big. That's 1/32 of your memory, I guess. And instead, you condense that by keeping a cache, which is indexed by the low bits of the branch. Let's say the low 10 bits of the branch. You've got 1,000 of these bits. And each one of those bits say whether or not the branch instruction at that location branched last time you executed it. Now notice that this cache doesn't have to be perfect. If there are two branches somewhere in the program that map to the same location in the cache, so you get the wrong answer. It doesn't matter. This is a probabilistic thing. As long as most of the time that cache produces the result for the correct branch, and most of the time that bit says which way the direction of the branch is going to go, then you've won. If it's wrong, then you just take a penalty for misprediction. So this version of the scheme is actually very simple, but it works only some of the time. Notice that we could have a case where a branch is taken almost all of the time, 99.99% of the time. You know, if it's the branch that ends a loop, for example, most of the time it goes back. But every time you exit that loop, you're going to flip the status of the bit, and that bit is now going to say not taken. Having done that and exiting the loop, you took you failed in your prediction because you thought it was going to be taken and it wasn't. The first time you enter that loop, you left that bit saying that the branch is not going to be taken. So the first time in the loop, you wind up mispredicting it. So even though 1 out of a million times the branch instruction branches, every time you enter that loop, you're going to take 2 hits in the sense of predicting incorrectly. So the next way to complicate it is, in fact, to keep more than one bit of information. Notice that if you view what we've done up here as a state table, basically the state of a branch is always in one of two states. We're either predicting it is taken or predicting it is not taken, and we bounce back and forth between those two states based on whether the last execution was taken or not taken. Well, instead of having 2 states, we can elaborate that to 4 states or 8 states or an arbitrary number of states that counts how many times it was recently taken. So if you start off with a a non-taken branch and you take it once, well, then it's weakly non-taken. And you might still decide to predict it to be not taken, although most recently it was taken. And with 4 bits, basically you have to take the branch twice until you decide that you should guess that it's not going to be taken. Did I get this wrong here? Huh? Oh, I got predict not taken twice. That's interesting. Okay, there we go. So you have to take it twice before you're into a state where you're going to predict it as taken. If you take it 3 times, then in fact you're in a state where you're predicting it strongly as taken, and one not taken will not make you change your prediction. With this kind of a scheme, in fact, this loop branch works much better in the sense that you only have 1 failure every time you execute the loop instead of 2 failures. The other more complication that you might want to add at the same time is, in fact, to make this cache a true cache, in the sense of adding to the value part of the cache a tag field that identifies exactly which branch it is that you've recorded the information for, so you don't misidentify one branch with another branch. Well, if you want to do that, then here's the hardware you need to do that. I know we haven't talked much about caches, but I assume you've seen basic cache organizations in other courses. And this is a kind of a classic cache. We're addressing the cache with the branch address. We peel off some low-order bits, I don't know, 10 of them maybe, so that we have 1,024 of these entries. We read out that value. The tag field contains the rest of the branch address bits, the high bits, so we can see if that element of the cache table was in fact the branch address we're talking to. So that tells us whether we have a hit or a miss in the history table. And then we read out the part that we really want, which is this counter. So this might be this 2-bit or 4-bit or 6-bit counter that keeps track of the history of the last history of the execution of that branch that we use to make our prediction based on. So let's take a look at some numbers that see how good a scheme like that does. This chart shows the misprediction frequency as on the previous chart for the constant case of assume a backward taken and forward not taken, and a profiled case, and then a non-profiled case which uses the 2-bit branch history table that we've been describing. And basically what you see is that the 2-bit counter does at least as well as the profile, and in fact in some cases does significantly better. If there are phases of the program where sometimes the branch is taken a lot and other times the branch is not taken a lot, the profiled case, which just records a single bit, won't follow that behavior, but the branch history counter, which records most recent history, in fact does. So in fact, we've done with this little bit of hardware at least as well and maybe better than the profiling case. People have done lots of simulations of this, and it turns out that 2-bit counters are almost as good as anything bigger than that. Keeping more history than 2 bits or more than 4 states is probably not a worthwhile thing to do. And it also is probably not worthwhile to go crazy over the number of entries. That 512 or maybe 1,000 entries are getting close to the best you can do. And if you want to get up as high as 4,000 entries, then you might as well stop there, because an infinite number of entries is not going to do any better for you. Now notice that even if we don't get a hit with not necessarily taking a penalty, remember that the percent correct, the number of times we get the correct prediction for the branch, is the amount that we hit in the cache times the amount of time that the cache says the right answer, that tells us we're correct. But then there's also the number of times we don't hit in the cache, and some of those we might be lucky. So there's some amount of time where, even though it's not on the cache, we made the correct constant prediction. So if we're hitting 90% in the cache, and 90% of those numbers are correct, we might still be lucky 50% of the time, or something like that. So the overall correctness is, what, 0.81 plus 0.1 times 0.5, or 0.86. So we gained a little just by being lucky in the case where we didn't actually make a hit in the history table. Okay, how else can we make this even more complicated?
Quick question.
Yeah.
What is the profiled case again? That's after one run?
Yeah, the profiled case is you execute the program once and you keep track for each branch of whether it branched more often than it didn't branch. And then you feed that back into the compiler, and it marks each branch instruction saying whether it goes or doesn't go most of the time. Basically keeps an average history over the whole execution of the program. Here's an interesting approach that the book describes and some machines have actually implemented, which is to base the decision for a particular branch not only on that branch, but on basically some sense of history of where it came from, what the sequence of branches were that got it to that place. You'd like to record some information about the program traces, but that's too complicated to do. So one thing you can do is just look at the m previous branches. Let's say you keep track of the last 2 or 3 branches and whether or not they branched. In this case, we're keeping track of 2 previous branches. We're keeping track of the branch before the one we're looking at and the branch before the one we're looking at, and marking whether or not they were taken or not taken. And all this is a shift register. Every time you do a branch, you shift it to the right one and you put the new status of the most recently executed branch into the left edge. And then basically you have 4 branch history tables, each one of which is a 2-bit branch counter just the way we did before. But this tries to model the fact that you may have gotten to our branch from 2 different paths. And depending on which path you came from, the decision about which way our branch is going to work, the current branch is going to go, may be very different. And in fact, this can't be worse because you've not lost any information.
Yeah.
In fact, yeah.
Aren't you going to find a cache with no history in it more often? Because there's 4 different ones there, so you're going to find an empty. You're going to.
Okay. You're right. There are more cases where you will find an unfilled value, although in some sense there's no such thing as an unfilled value. You start off in the initialization sense with something in all of the arrays, so you make some prediction. But you're right, there may be, at least initially, more values that were not sent based on branch history. And in fact, what I said was wrong. I can invent pathological cases where this would give you worse results than having only a single branch counter for each branch. But in fact, people have modeled this, and in fact, it does better. And you can imagine elaborating this by keeping history of more bits, more branches, and or putting more bits in the branch counter. The only implementation I know of this for the IBM Power 1, in fact, used this scheme, which was looking at 2 previous branches, and for each table entry, you kept track of a 2-bit branch counter. Let's look at some delays and pipeline calculations for how one might go about doing some calculations for whether or not what the effect of these tables are, the branch history tables. Let's see. Let's assume that, to make life more interesting, that unlike DLX, the control point, the point at which we understand which way the branch is really going to go, is in execution, not in ID. And let's assume that we're not going to use a delay slot. And let's assume, we've got too many uses of the word predict here. Let's assume that we will assume that the branch is not taken if we don't know anything else. Now let's compare that scheme, which doesn't do any branch prediction, it just does some static branch assumption, and see what effect we get by adding prediction in the ID phase. Now remember, we want to get this branch history table to occur as early as possible. So we want to have it ideally occur in the ID phase and make our decision there. But if we don't do any prediction at all, if we make our assumption based on the static factors, the static assumptions, since we're assuming not taken, the not taken penalty is 0. The taken penalty is 2. Remember, it's 1 more than DLX because we're doing the branch decision in execute and not an ID. So with no prediction, the penalty is 2. If we predict that the branch is taken and we predict right, there's a 1 cycle penalty. And in fact, on the next chart, it shows how that is. Our branch instruction is here. We've already fetched branch plus 1 in the next cycle. If we predict at the end of ID for the branch that this branch is going to be taken, then we can start fetching that target at cycle 3. So we've paid a 1 cycle penalty. If in fact we predict wrong, then we'll know that at the end of execution time. So if we predict it was taken and it was incorrect, then we have 2 instructions to nullify. One is the original one, which was the instruction following the branch. The other was the target instruction that we fetched because we predicted that we were going to take it. And then we decide that that prediction was wrong, so we have to go back and refetch the instruction following the branch. So in fact, we suffer a 2-cycle delay. If you really want to be clever, then in fact you could sort of save this instruction just in case your prediction was wrong and at least perhaps save another instruction fetch. But if you don't do that, then you're going to suffer a 2-cycle penalty. If we predict that it's not going to be taken, and we predict that correctly, then in fact we suffer no penalty. It's a sort of normal case. So, how good does our prediction have to be before this is a win? Well, let's say that on the average the percentage of branches that are taken are 60%. If we don't do any prediction, if we don't do any of this branch table stuff, then 60% of the time we're going to suffer a 2-cycle penalty. So on the average we're going to suffer a penalty of 1.2 cycles. If we do this prediction stuff, then if we're right, then since 60% of the branches are taken, 60% of the time when we're right, we will suffer a 1-cycle penalty. When we're wrong, then we're going to suffer a 2-cycle penalty. So the question is, how high does percentage right have to be before our loss doing the prediction is less than our loss with the prediction? Notice the problem is that if we predict wrong, then we suddenly have a 2-cycle not taken penalty. If we did no prediction whatsoever, then we had a 0-cycle not taken penalty. So this could be a loss for us. But in fact, the answer is about 57%. And most of the branch prediction strategies can do at least better than 57%. So at least with this set of assumptions, it's pretty easy to get this prediction to be a win. But it's not guaranteed. Okay? How can we do even better? Well, one of the problems with what we just did is that even if we made a correct prediction that the branch was taken and we predicted it to be taken, we still have to suffer a 1-cycle penalty. The question is, can we do any better than that? Now that 1-cycle penalty is because we don't know until the ID stage what the target address is. In fact, if we could figure out at the end of the instruction fetch what the target address of the branch is, then a correctly predicted taken branch would cost us no cycles. Well, the way to do that is twofold. One is to assume that we can stick this branch target buffer stuff into the instruction fetch stage. Well, there's no reason why you can't do that. It doesn't depend on whether or not it's a branch instruction, as long as the tag really identifies it as the correct instruction, as the branch instruction. So we do need the tag, which was sort of optional in the previous case. Now we really need a tag because we really want to know whether this is a branch instruction. But if that's true, then we can put all of this cache lookup logic into the instruction fetch stage. At the same time this maybe branch instruction is being fetched, we're looking up the information about it in the branch target buffer. So we fetch out of that buffer the same kind of counter we were doing before, indicating whether or not we think it's going to branch. The other thing we add is what the address of the target is. So in fact, you don't even have to wait for the branch instruction to be decoded to figure out what the target address is. So if it's a hit, which is to say if this cache entry contains the address of the branch instruction, and if the counter is greater than 1 for a 2-bit counter, that indicates we are guessing that it will branch, then in fact we begin fetching at the end of the instruction fetch stage. And in fact this represents a 0 penalty for taken branches. If it works.
So
Self-modifying code.
If you're allowed to write on your code, you could be...
They chop off your hands if you write self-modifying code. In the old days, that used to be great fun. In fact, that was one of the real problems for the 36091, because that architecture encouraged you to write self-modifying code. There were string move instructions that had lengths in them, and it was sometimes convenient to store the length into an instruction a little bit further down in the instruction stream in order to get the right length into the instruction. And that really created havoc with machines like, well, any of the pipeline machines, including the 36091.
question?
Yeah.
So the target address in this table, is that written from the previous time? I mean, at some point that address has to be calculated, right?
Yes, that's
so
written.
You're having to go back and update this table?
That's right. That's well, as you have to update the count. After the branch is actually executed, you need to update the cache entry to keep the counter current. And at the same time, you update the cache entry to keep the target address current. But it's still not perfect. I mean, there are problems. What if it's a jump and link register or jump register instruction, where in fact the target address of that jump might change every time you execute it? Well, it's not going to work so well. In fact, the next slide shows some pros and cons of the branch target buffer. The biggest pro is that in fact, if things are working right, then you get a no loss predicted correctly, no penalty for a correctly predicted taken branch, or not taken branches like before. But it doesn't work well for indirect branches or jumps, things that go through registers. You've got to store the full target address in the tag of the cache to know that it's a branch, so that makes it big. It's lots of bits. Some people have done some studies to look at if you have a constant number of bits to devote to this kind of logic, what's the best thing to do? And it might be, in fact, that the best thing to do is to build a bigger branch history table and not necessarily a branch target buffer. But those kinds of studies vary a lot depending on what programs you're measuring and what your other assumptions are. Notice something fascinating, that you're storing the address of the target instruction, the instruction you want to branch to. Why store the address? Why not store the instruction itself? So in fact, when you do a successful branch, you don't even have to fetch the target instruction. It's already in the branch target. And that essentially allows successful branches to take 0 cycles, not even to have no stall cycles, but in fact to take 0 cycles. And I don't know if anybody's actually done this, but it's certainly been proposed as a way to make time go faster than we could otherwise.
So the branch instruction would essentially just be replaced by whatever the next instruction was.
That's right. That's right. Lots of recent machines have used branch target buffers. The PowerPC 601, the Pentium does. The PowerPC has a branch target cache, and in addition has an even larger branch history table with 2-bit counters to get a combination of both effects. So this is technology which is very actively in use. Next time we will go on to another topic, which is how to design machines that in fact issue instructions faster than 1 per cycle. See you then.